Good afternoon, CS109. How are you guys doing today? Yay, it's the day before Thanksgiving. How are you guys feeling? Okay, it's got to be nice to have a little bit of a break coming up. We have an exciting class today. We're going to be talking about naive Bayes. It is not only one of the things that you will be implementing on your final assignment in CS109, but it's going to be our first machine learning algorithm that we learn about in CS109. Exciting day. But it's a Friday, so because it's a Friday, I was going to tell you guys a little bit of story. And I was going to tell you a little bit of story of my lovely daughter. So this is my lovely daughter. And I think you guys know I have a daughter at this point. But you know, there's so much I can say about it. Like, wow, parenthood, what an adventure it's been. I've learned so much more in these last year and a half than maybe I learned in an entire PhD about life, how people learn. It's just been such an exciting time, you know, how to teach people boundaries. But there is, you know, I would love to share something interesting that we've also gone through as parents that not every parent goes through, which is when very young, so she was born as this crazy experience, and then the next 2 weeks were like this sleep-deprived bliss of like this brand new soul in the world. But then when she was 2 weeks old, we got some interesting news. We found out at that point that she was born not able to hear at all, which is surprisingly common. About 1 in 1,000 babies this happens. And you know, there wasn't a family history, so it was a little bit surprising for us. And again, I feel like I immediately learned a lot. It wasn't what we expected, but boy, do we learn so much. First, we learned sign language. We learned about this whole new wonderful culture that exists in the US and around the world. We learned a little bit about, as a parent, not having clear expectations for the life your child's going to lead. Like, they're always going to lead different lives than you designed for them. They get to choose. We're learning a lot about that at week 2. But then also an interesting thing is, you know, she has these things called cochlear implants, and you guys might have heard of those before. Basically, she has a microphone, and that microphone goes to a processor. The processor goes to a coil. The coil sends a little signal to a receiver on the inside of her head that's connected to her auditory nerve, and it stimulates her auditory nerve. So basically, it's a microphone that stimulates directly this thing in the inner part of the ear. And it's incredible. If you didn't know, the biggest breakthrough in this device happened here at Stanford. Actually, in the EE department, they figured out a whole bunch of key ideas to make this possible in humans. And now she hears so well. Now, it's such a hard story to tell because I was so ready to embrace not hearing. Like, signing was the coolest thing. And I was really excited for that journey too. But now it looks like our journey has hearing and talking and dancing. In fact, every day starts with a dance party at 6 a.m. But you know, I must say that's like one of the things that I'm very thankful for. So going into Thanksgiving, I'm just so thankful to have this wonderful soul in my life who's taught me so many things. I am also thankful for the people who worked hard in technologies to give her access to this one facet of life that I have enjoyed. And you know, also thankful for all the dance parties and the hugs. So that's my Friday story for getting us started. Bring us back into CS109. We are having this wonderful capstone experience in CS109 where we are building up towards learning some of the fundamental algorithms that are currently changing the landscape of computer science and artificial intelligence. We will be working up towards deep learning, aka neural networks. To get there, we are going to start learning some algorithms on computer science. And we've done a lot of work. We've built a strong foundation of the core theory that you need to know. And now it's time to celebrate. Use that core theory to learn the algorithms that are powering the technologies that you hear so much about. And today is going to be that first so exciting days, and we're going to pick off one of these 2 critical AI algorithms called naive Bayes. Now that we're getting to machine learning, I thought it'd be helpful to just give you a picture of how machine learning fits into the world of probabilistic models. A lot of times we think of machine learning as being a probabilistic model. You'll imagine getting some inputs, and then your probabilistic model will have some parameters, and based on those parameters, it will make a prediction. And it'll often do so probabilistically. And these parameters are just like all the parameters we've seen in parameter estimation. Really, you should still think about them as sliders, and if you had the perfect settings for these sliders, you'd have a good probabilistic model that could do this input-output prediction quite well. Parameter estimation is that art form of setting sliders. And that art form setting slider is going to be the core theoretical basis for making good probabilistic models. And we really have two great ideas for how you could set those sliders. The first great idea is maximum likelihood estimation. You're going to choose the slider values that make data in a training data set look as likely as possible. And you work through some of the math. That means we're going to set our sliders using this beautiful little equation. That's only one perspective, and on Wednesday's class we saw a totally different perspective. And the totally different perspective was, instead of choosing the slider values that make the data look as likely as possible, we're going to choose the most likely slider values given the data that we've seen. And they're both defensible. People use both of them. They have just one big difference when you get to the final equation. In MLE, we're just going to have the log of the likelihood, and we're going to be choosing the parameters that maximize this. In MAP, that's the fancy version for the Bayesian idea of choosing the most likely parameters. You have basically the same equation, but you now are also going to have a term that's related to how likely you thought the parameter value was to take on its current value before you saw any data, a prior. So you have a Bayesian prior, and it's just like the prior in any of your Bayes equations that you've seen before. And you'll have a term for that prior, and the rest is exactly the same. And so realistically, these aren't all that different. And the biggest 10 out of 10 takeaway is you now have tools that could allow you to take data and any probabilistic model and choose good values for parameters. Important notation, though, that we're going to see a lot is even though there's always random variables, like for example in this MAP equation, there should be a random variable for the parameters. There should be a random variable for the first data point. There should be a random variable for the nth data point. And realistically, the probabilistic statements should be talking about equalities of the random variables taking on specific values. It's too much to write. Nobody writes out the full expression. Instead, people will often write that same expression using shorthand like before, below, where you say, how likely are the parameters given the data points? It implies that there is a random variable for each of these non-random observed variables. So like x1, that's the observed x1, and it's implied that we're talking about the event of the random variable x1 taking on that value. I don't want to confuse anyone on notation. Certainly in lots of other probability classes, they'll just show you this and work with it, and people will just be like, okay, great. It's the likelihood of the parameters given the data. If you want to get really, really specific, this is the slide that you could use for making sure you're understanding the notation. In this review, I did want to just give you another perspective on MAP, and I wanted to combine it with what we learned about with betas. So in a beta distribution, you're estimating a single parameter, which is the P of a Bernoulli, or a binomial. And where you're estimating that P of binomial, after you've seen data, and after you've incorporated your prior, you calculate what we call the posterior beta. And beta distribution's story ended there. Maximum posterior, if you were estimating that particular parameter, would then take this posterior and it's just going to choose whichever argument maximizes the likelihood of the parameter. That's also called the mode. So the mode is the value that is most likely. Okay, I'm almost done with review. And maybe if there was just one thing to really focus on in this review, it would be this takeaway about MAP for Bernoulli. So when we learned about betas, we said, if you're estimating the P of a Bernoulli or a binomial, same thing, you can imagine that before you see anything, you could have your belief in the probability expressed as a beta. Then you see some data and you end up with what we call the posterior belief, your belief after data, and that was a beta as well. And if you took the mode of that beta, then you get the MAP prediction, which is given by this little formula. It leaves this question for the user, which is, what was your prior belief? Can I just give you the prior belief that I always use if I don't have any other reason to choose a different prior? I use a particular prior, which is a beta 2,2. That's imagining one imaginary success and one imaginary failure before I see anything. And with this particular prior, you end up with this particular posterior, and the MAP estimate is just this simple equation. So, how many successes did you see in your data? add 1 to that, and divide that by how many successes plus how many failures plus 2. And it's just a very, very, very reasonable estimate. This particular prior has a fancy name called Laplace prior, and Laplace prior is just a fancy way of saying 1 imaginary success and 1 imaginary failure before you get going. Yes, question?
Yeah, I was just going to ask, is there a particular reason why you pick 2-2 instead of 1-1?
Yeah, because of the beta. Oh my gosh. Like, if somebody says beta 2-2, so a beta 2-2 means that alpha equals 2. Do you remember what alpha was? It was number of successes plus 1. So 2-2 means 1 imagined success, 1 imagined failure. If you had beta 1-1, that's 0 imagined successes, 0 imagined failures. The Laplace actually has a really good intuition for why you don't want it. Or sorry, why you would want the Laplace. You could never end up with a probability of 0 or a probability of 1. And for some reason, it's like, no matter what I'm estimating, whatever I'm estimating a probability, I never want to think it's impossible. And 0 or 1 can represent different versions of impossible. But because of that, Laplace has that nice property. It's the least assumption you can make, guaranteeing you'll never get a 0. So you maybe never get a divide by 0 in your equation. Okay, good question. So, yes?
I don't really understand what MAP is. Like, is it like a beta distribution, or is it like a way to get like the beta thing?
So, MAP at its core is a philosophy. It is a philosophy for how to estimate parameters in general. If you applied that philosophy to estimating the parameter p in a binomial, you would end up with the beta. And you would end up with not just the beta, but you would end up with this posterior. That's assuming a prior, but with this prior and the MAP philosophy applied to the Bernoulli, you get this posterior.
So beta is just like a way of like having this belief and updating it based on the belief, and MAP is that.
Yeah, and MAP, they're so related. MAP will just choose one number, whereas the beta represents a whole belief distribution. But they're so related because they're both doing the exact same Bayesian thing. Good question. Okay, so, and big picture, philosophically, we have 2 ways of setting parameters, and both of them give us numbers for every parameter. They don't give us distributions, they actually give a cold, hard number for every single parameter they're supposed to estimate. Okay, and that's what we've got for review. Shall we jump into it? Let's see some machine learning. So we've got our last estimator, and it's time to start thinking about machine learning. Let me introduce you to the tasks you are going to be able to do on your final problem set. On your final problem set, you're going to write 2 machine learning algorithms, and those 2 machine learning algorithms can all do tasks that will apply to these different data sets. All the tasks are going to have training data, and the training data is going to have both inputs and outputs. I'll talk about that a little bit more. This is how I could introduce it. Sorry, these aren't updating fast. Sorry, I could introduce it with these equations, but let's come back to these equations and let me explain to you what these equations are saying. Let's imagine your task is you have some input movies and whether or not users like them, and you want to predict if the user will like a particular output movie. Does that sound like a reasonable task? For every single user, you'll be given a whole bunch of training data. And in that training data, you'll be given historical users. And for every historical user, you'll be told what movies did they like, and you'll be told the truth about whether or not they like the output movie. We think about this as a tuple, a combination of the input things that you would use for your prediction and the true label of whether or not, for this historical example, the person actually did like the movie. And I'm going to give you a whole bunch of these, and your machine learning task is to build a little system that could take the inputs and predict the output. So, let's be clear. The inputs in this case are all of these movies and whether or not the user liked them. And the output is whether or not the user liked a particular target movie. In this case, it's miscongeniality. Now, a little bit about notation. Notice how our inputs are x's and the thing we're trying to predict is y. I will always be consistent about that. Notice this superscript I. That means the ith person in our training example. And there's a very specific reason why we use superscript for I and not subscript for I. And we'll use this notation. In 229, they'll use this notation. 221, they'll use this notation. It's because you see this X, it's a little bit weightier than the Y. It's bold. And does anyone know why you would bold a random variable or a variable in general? Yeah.
It's a vector.
It's a vector. Why is it a vector? Because vector is mathematics for a list. And it's a list of numbers. It's not just one number. The X itself has a whole bunch of numbers in it. Because of that, when we're writing it, you'll sometimes see it bold. And there's just one other thing I'd like to say about that vector notation, which is, since xi is a list, you may want to talk about a particular element in that list. And this is what the notation looks like. And I'm giving you the full professional version so that in later classes you'll be able to follow along using the exact same notation. But if you want to talk about this particular value, well, it's from the ith user, and this could be the jth value. In this particular case, it's user number 2, and this is movie number m. And because we use the superscript, it's easy to differentiate between the particular training data point we're on versus if you want to talk about a particular location within the list, which is the inputs. Notation can be so complicated. Please, what's confusing about this? Yeah.
So if we were to apply this to this case, the superscript would apply to which row are we on?
This
And
is
then-
row 2.
And then the subscript is what column with that row.
Exactly.
Okay.
Exactly. And hey, notice this. Computer scientists like to be 0 index and mathematicians like to be 1 index. It's caused all sorts of bugs everywhere. But just know that. By 1 index, I mean they often think about user 1, user 2 in notation. Okay, great. So we got some notation. And the beautiful thing that we're going to do is we're going to talk about a lot of different interesting tasks you might do that all have a very similar format. Another task you might care about is we're going to look at different regions of interest, that's what ROI stands for, in someone's heart. And based on whether or not we see abnormalities in those regions of interest, we're going to predict if they have a healthy heart or not. So again, this follows exactly the same format. If I talk about input, so X, from the first person and the second value within that list, I might be talking about this particular number, which is a 1. So if I talk about this whole second person has two things. They have all their inputs, the regions of interest from which we'll make our prediction, and the output. You're told whether or not this person had a healthy heart. To be clear, the interesting thing about this is going to be, based on this training data, you make a machine so that if someone doesn't tell you whether or not somebody has a healthy heart, you can predict it. So you're going to build a machine that can take inputs and make a prediction about the output. Yeah?
So just based on these two examples, it seems like everything is quite binary, isn't it? It's just like a true or false for both the inputs and the outputs.
Yes.
So if we were to make it not binary, so for example, for the movies, there was like some sort of rating that they could get, how much more complicated would it be?
You know, it's a good question. Not that much more complicated. So the question was, hey, Chris, I noticed that everything's binary, and you're astute. Everything is binary. I'm going to keep it binary because I want to explain all the theory, kind of keeping things as simple as possible. And then your question was, if you want to break that assumption, how much more complicated will it be? Well, once you see the algorithms, you'll realize not that much more complicated, though it is so helpful to understand these algorithms just thinking about the simplest case, which is binary. Yes?
ROI images that are going in, are you just looking if like that feature is present on the heart, and how does that actually work?
So this is a real data set from real people's hearts, and what doctors would do is there'd be different specialists who could look at different regions and say whether or not it was healthy, or whether or not they saw something. And no specialist was able to predict healthy hearts, but if you took all the specialists together and their perspective on each region, it turns out that people were able to make much better predictions about healthy hearts.
So the output is just measuring whether the hearts overall are healthy. It's not like given a new heart and then testing if that's healthy.
Yeah.
Okay,
So,
got it.
but once you build this machine, you could imagine a new person comes in. Doctors look at each of the regions of interest. We put those numbers, those ones and zeros, into the machine, and it says this person's got an unhealthy heart. We need to go look further into it. Yes. Great question. A little bit more on notation, just to make sure we're following along. If I talk about x2, that's the input for the second person. And if I talk about y2, that's the thing we're trying to predict. And it's the label that we were given in the second training example. Okay, and then another data set was ancestry classifier. So some companies can look at DNA and they can predict our ancestry, and the sorts of data they have is whether or not there's a change at a different particular nucleotide location. We don't have to worry too much about that, but you'll be given M different nucleotide locations, and for each user you'll say whether or not they have a change at that location, and then you'll have an output of particular ancestry that you might want to predict. To the question that was asked earlier, everything I showed you was binary, and certainly there's lots of algorithms that break this. You could have continuous values, you could have discrete values, you could mix continuous and binaries, you could predict things that are non-binary. There's lots of cool extensions of this, but first understand the core with binary, and then it'll be easy to talk about these extensions. So, bringing it all together, this is how the problem's formulated. I'm going to give you a bunch of training data, and from that training data, your job is to build a classifying machine, a machine that can take in an input and predict an output. Every training data is an input-output pair, so we call it labeled because it's like I gave you the input and I label whether or not it's a 1 or a 0, and I give you n of these. We talk about how many features your training data has by looking at any input and saying, how long was that list? How big was that vector? And that's how many features we say your training data set has. Okay. Machine learning is this process of taking training data and learning parameters for a probabilistic model. And it's ubiquitous. This is one particular version of machine learning that we call classification. And we call it classification because you're predicting a 1 or a 0. You're predicting the y, and since the y is like one of a small set of classes, that's where we get this name classification. There's other versions of machine learning. Maybe you're predicting continuous numbers, maybe you're predicting actions. There are other versions, but classification is the heart and soul and where it all starts. One metaphor I have for this task you are given is you're making the Harry Potter sorting hat. And I love to think about this, like everybody is like curious about this Harry Potter sorting hat, what would it be like to see it? And in Stanford, not only do we get to think about it, but we get to learn, what could possibly go into making your own sorting hat. This classification algorithm that we're going to, use the sorting hat as a little metaphor for, you can imagine it looks at some input, so it gets this list of features, 0s and 1s, and its job is to predict a label, a 1 or a 0. Are you guys following along the task? Ask questions if there's anything confusing. Certainly worth clarifying before we jump into how are we going to solve this? Yeah, naive Bayes, yes, certainly is how we're going to start by solving this. Okay, so we've got these 3 different problems. Let's jump into one of them, the Netflix one, and let's think about this a little bit. So, I've got a very simple version of this problem. My version for you is that for every user, there's only one movie in the inputs that we're going to look at, Independence Day, and the output is going to be predicting if somebody likes Life is Beautiful. So every single value in our feature, it's a 0, 1. To be clear, every single value in our predictions either a 0 or 1. 1 means they will like the movie, 0 means they won't. And I'm going to gently start us. How could we build a machine learning algorithm to do this task if you only had one feature input? And I have an algorithm for you. It is called brute Bayes classifier. And no one ever uses this algorithm, but my promise for you is this is easier to understand. And if you understand this and you see why it breaks, then understanding naive Bayes will make a lot of sense. So you guys want to hear my total hacky algorithm? Here's my hacky algorithm. We are going to build this machine. It's going to be a probabilistic machine learning machine, and it's going to take in inputs whether or not somebody likes Independence Day, and it's going to predict an output whether or not they like Life is Beautiful. Now, in general, the input will be more than one number, but originally, this input is just going to be a single 1 or a 0. What I'm going to put into my machine is I'm going to have a little function which calculates how likely is it that the output is a 1 given the inputs I observe. And if the probability that the output is 1 given the inputs I observe is high enough, then I'll predict a 1. And particularly, I might do this. If I could say, put a 0 into this, and if I put a 0 into this and it says the probability that y equals 0 given the inputs I observe is 0.62, then maybe I should be predicting a 0. Does that make sense? I'm just going to figure out the probability of the output given the input. Straightforward, right? Seems like a reasonable thing to do. You gave me an input value, I calculate the probability of the output, and if the probability of the output being 0 is greater than 0.5, I predict 0. Otherwise, I predict 1. Now, hopefully if I put in a 0 and I got 0.62, then if I put y in as 1, the probability that y takes on the value 1 will be whatever makes those two things add up to 1. Making sense? Yeah.
So when you say output, does that mean specifically 1 or 0 or any output at all?
Yeah. This whole machine learning algorithm has to give back a 1 or a 0. 1 meaning you think they're going to like the movie, 0 meaning you think they won't. So classification, you don't have to give me anything other than a 1 or a 0.
But the probability of either doesn't matter in the output that's given.
Yeah, I'm just going to use the probability as a step to get to the answer. If the probability of y equals 1 is less than 0.5, then I predict 0. So it's a step towards my final answer, which will be a 1 or 0. Very good question. Okay? Now, to put this a little bit mathematically, one way of saying this is I'm going to choose a 0 if the probability that y equals 0 given x is greater than if you put a 1 in for this. So if you put in a 1 for probability of y equals 1 given x, if that's larger than if you put a 0 in for this y, then we're going to be predicting a 1. So just in some notation, I'm just going to say it's the argmax over my choice of y's, whichever one is larger for the probability of that value given x. So here's how I want to make my prediction. It's either going to be a 0, 1, and it's going to be whichever one makes this probability large. So just to be clear, y hat is going to be a prediction, will they like Life is Beautiful? And x is going to be whether or not they liked Independence Day. And I call this brute force Bayes because it turns out maybe estimating this probability is a little hard, so I'm going to use some Bayes' theorem. Just to be clear, if y equals 1, that means they like Life is Beautiful. So I'm going to use some Bayes' theorem here. I'm going to say, okay, this is the same as if I took that term and I replaced it with Bayes' theorem. The probability of x given y times probability of y divided by probability of x. Beautiful thing about argmax is that argmax doesn't care about constants. So this normalization constant on the bottom, it's a constant. It doesn't change as y changes. Therefore, it doesn't affect whichever 0, 1 is going to be the argument which maximizes this expression. It goes away. Fantastic. So I haven't done too much here. I've just basically done, I'm going to do Bayes' theorem, and I'm going to get rid of the normalization constant because normalization constant gets lost in the argmax. Questions about that? Such a weird thing, the normalization constant. Like, y doesn't change as you put in. If y was 0 or y was 1, it's crazy to think that the probability of x doesn't change. That's mind-blowing. But I promise you it doesn't change. It is a constant. That's why it's got its name. And because it's a constant, it doesn't affect the argmax.
I don't really understand why you go from probability of y given x to argmax of y given.
Oh yeah, because the output of this little machine isn't supposed to be a probability. The output of this machine's got to be a 0 or a 1. And so the argmax is just a really fancy way of saying, I'm going to turn this probability, which is a continuous number between 0 and 1, and I'm going to just discretize it into either or 0 or a 1. That make sense?
It will eventually.
Yeah, if you go back to the machine. Okay, here's my claim. No, it should make sense. The machine doesn't give you back a probability. This machine's got to give you back a 0, 1. So if you can calculate the probability that y equals 1, you're not done. You have to do the simplest thing. If you figure out the probability that y equals 1, like let's say I told you the probability y equals 1 is 0.7. What do you predict? Oh, no, much easier. I just tell you that, like, based on your x, I told you that the probability that y equals 1, so if I say the probability that y equals 1 given the x that you observed, If I tell you that this number is 0.7, I'm telling you that based on your inputs, the probability that the output is 1 is 0.7. You have to predict something. Do you predict that y is 1 or 0?
1.
Yeah, so this gets turned into a prediction of 1.
So it rounds it up.
Kind of, yeah, exactly. It's like argmax is a fancy way of saying round it up. Now, argmax is a little bit more elegant than just saying round it up. The reason argmax is a little bit more elegant than rounding it up is it's saying, well, I'm going to choose whichever one's bigger, y equals 0 or y equals 1. And the reason it's nicer to put it as an argmax is exactly this part, where round it up wouldn't allow you to get rid of a normalization constant. Whereas argmax, which is doing the same thing as rounding it up, has this really nice property that if you ever have a constant, it just doesn't come into your equation. And you don't have to bother calculating probability of x. Good question. Does it make sense now?
Yeah.
Okay, fantastic. Great, that's critical. If there's something that doesn't make sense, just tell me. This is not too much content in this lecture. I just want to make sure everybody understands it. Because you're going to have to code it up. Okay, so here's my brute force Bayes. It's just our warm up to naive Bayes. And the simple idea is I've got a tiny little probability engine, and it's going to predict 1 or 0. Now, in order to do this, I need to be able to know these terms. I have to know the probability of y equals 1 and the probability of y equals 0. And I have to know the probability that x equals 0 given y equals 0, the probability x equals 1 given y equals 0, probably x equals 0 given y equals 1, and probably x equals 0, 1 given y equals 1. So what are the parameters? I told you machine learning, you'd have these little, probabilistic machine. We'd estimate the parameters, and then using those parameters, we could make predictions. Where are the parameters here? And my answer for you is that the parameters are in these two things that you have to calculate. Your brute force Bayes is going to make a prediction based off these. And so you need to be able to, when you're coding this up, you have to say, what's the probability that y equals 0, and what's the probability that y equals 1? And then for any value in this conditional probability table, if y equals 0 and x equals 0, you need to say, what's the probability that x equals 0 given that y equals 0? So you need 1, 2, 3, 4, 5, 6 parameters. And if you could estimate all these parameters from your training data, then you'd have a probabilistic model and you could make predictions. I'm going to take a moment here, now that I've told you about the parameters, and I want you to talk to the person next to you, and I want you guys to do one of those, ask the person, hey, what's confusing about this, and see if you can generate a good question for me. So what's confusing about this? Here's my parameters. Think about it for a second with the person next to you, and then we'll talk about it all together. Okay, go for it. Okay, hopefully that was a good chance to come up with a good question. I took that moment to write up. There's kind of 3 critical random variables here. X, the input movies. In this case, Independence Day. Did they like the input movies? And that will take on some values. Y is, do they like the target movie? And I just want to point out that Y and Y hat are slightly different. Y is do they like the target movie, and Y hat is your prediction for whether or not they like the target movie. And so we do have slightly different notation for predictions versus the actual truth. Okay, questions that came up? Yes?
We were wondering why you had 6 parameters to be like, that we need to find, instead of just like 4, because we have 4 data points.
I could have a lot more data points. I could give you hundreds. I could give you, actually this is Netflix. I got 1,000,000 data points for you, no problem. So I have 1,000,000 data points, but there's still another question, which is like, do you actually need all these parameters? I could hone in on these 2 parameters. If I told you that this number was the probability that y equals 0, if you wanted to know probability y equals 1, but you knew the probability that y equals 0, could you figure it out? There's a little bit of redundancy here. We're not going to worry too much about it, but you could have a slightly more compressed parameter set if you wanted to. But this is the simple algorithm. We're not going to worry about optimizations.
Is the X vector here representing a single user or like a single data area?
Good question. So the X, on some level, when you train, you'll be given many users. And for each user, you could be given many movies. In this case, though, X is going to be for the ith user. So we're going to talk about, particularly for this is after you've trained. So a user comes in and they like list of movies X. And in this case, the list is just 1 because we're doing it for the simple case where there's only one thing we're basing our decision off of.
So if we wanted to do it, do this same thing, but for a ton of people, you would just basically for loop over this?
Exactly. You would just for loop over this and you make your prediction for each person. Yes, good question. Yes?
Wouldn't we also need a variable called x hat for that specific user?
You know what? That's a really good question. We're always told their history. You don't have to guess at their history because I tell you for X's whether or not they like this movie. There's no guessing involved.
So how is x different from the
Y?
Y.
Okay, good. X is I tell you this about the person, and you have to predict this stuff. So the X is the stuff you're told, and Y is the stuff you're predicting.
How is that different from Y?
So you're going to make a prediction, and we have 2 things to separate the guess you made and whether or not they actually turn out to like this movie. This is what we call unobserved. You generally don't know if they like the movie, and so you just make your prediction, and then maybe in the future you'll observe if you got it right.
Okay.
I just want to be clear about those 2 things. Yes?
Could you explain again how the 6 data is related to each other, probabilities?
Yeah, each of these is going to be a probability. And so there's all these different things. Like you should know the probability that X, whether or not they like Independence Day, given whether or not they like Life is Beautiful, you should know that probability. And if you know each of these probabilities, then we'll be able to calculate this expression no matter what X or Y are. If you told me each of these probabilities. So yes, we should estimate all of those probabilities. Every theta will be a probability. Do you want to know how we get those probabilities? Yeah, on some level, counting is a very good answer. And just to be clear, I'm going to put all these into a conditional probability table, which says, condition on Y's value, the probability of X taking on these values. And I'm just going to put it all into one little structure here. Okay, there is a question. How do you take your 1,000,000 users and estimate all of these probabilities? And then you just said it. You're like, counting. What a reasonable thing to do. MLE says you should just count. You can think of this as a binomial, and you're estimating the probability P. And MLE says just count. You'll say, what's the fraction of users who like this movie, given whether or not they liked the movie Y? And if it turns out nobody did, you'll get a probability of 0. And you could end up with a probability of 1 if everybody who watched this movie liked it. So MLE says just count. Figure out, what fraction of people who like movie Y also like movie X. MAP has a different opinion. MAP says just count, but since this is a binomial, like we talked about in review, you can add in your imaginary trials for your beta prior. And as I told you, the imaginary number of trials that I like to use is what's called the Laplace prior, which is basically you add in one imaginary trial for each outcome. So if y equals 0, I'm going to add one imaginary trial for x equals 0, and one imaginary trial for x equals 1. So you can imagine this here is a beta p for a binomial that I'm estimating, and I can use MLE or I can use MAP for it. MAP or MLE, they're both very, very similar. They're both basically just counting. It's just MAP adds in one imaginary trial for each outcome. At this point, I've given you a theory. I've told you how we can get training data and we can estimate the parameters. What I haven't told you is what it actually looks like to make our prediction. So let's just go through this. Let's imagine you've learned all these probabilities from data. You learned all your parameters. Here's how you could use it. A new user shows up and they like Independence Day. So that means that x1 is 1. And we can say, okay, we're going to argmax this, and we're going to loop over the value y equals 0 and y equals 1. Let's start with y equals 0. This expression, when you put in y equals 0, and you take into account that x1 was 1, becomes this. It becomes probability of x1 equals 1 given y equals 0 times the probability of y equals 0. And this is just going to be taking in two different numbers. Probability of y equals 0, we've got a parameter for that. The probability that x1 equals 1 given y equals 0, we've got a parameter for that in our conditional probability table. You just multiply those two things. Now we should also look into the case that maybe they do like life is beautiful. So if we set y equals 1, we can take, what's the probability that y equals 1? We know that parameter. And we can know what's the probability that x1 equaled 1 given that y equals 1? We know that parameter. And so we can just multiply those two things and we get a different number. This was the expression when y equals 0. This was the expression when y equals 1. What value of y is the argument that maximizes? You guys can just say it. But say it with confidence. 1. Yeah, fantastic. It is in fact 1. Notice how I don't change x. I was told that they like Independence Day. I'm not going to be messing around with x1. I know it's a 1. What I'm trying to guess is y. And so this argmax tries the argument y equals 0. It tries the argument y equals 1. Whichever one had a higher expression, that will be my output. So I'll be predicting in this case that y equals 1. They will in fact like life is beautiful. Yes?
This may not apply here, but should the law of total probability say that both of those numbers should be adding up to 1?
They will not add up to 1. Why don't they add up to 1? That's such an interesting question. You're right, they don't. Like, you're glancing at this is like less than 5, and that's 0.2. They don't add up to 1. Oh my God, did we do our math wrong? No, everything about this math was fine. What happened? An idea?
I think it's because we're not considering the case where they don't like Independence Day, and if we did, and we use all the conditional probabilities, then we'd get to 1.
It's a very good guess. It's a very good guess. That's not in fact it, but that was a very, very good guess. There's another thing that we got rid of. Wait, it's your question.
I think is it because we got rid of the normalization constant?
It's because we got rid of the normalization constant. This is no longer a probability. If this were to be the probability that y equals 0, you'd have to divide it by the normalization constant. Similarly, if you wanted this to be the probability that y equals 1, you'd have to divide it by the normalization constant. Because we got rid of those two numbers, they're no longer true probabilities, and it's no longer the case that this is the probability that y equals 0 and this is probably y equals 1. Instead, these are the expressions. Whichever one's largest will be our prediction. Yeah, question.
Why are we trying to predict x?
We're not trying to predict x. X is always 1.
Then why are we doing the probability like the Independence Day? I thought we were trying to work out the probability of life.
Yeah, it was just, Bayes' theorem flipped that conditional. So Bayes' theorem said it's going to be the probability that like Independence Day given whether or not they like y.
We actually have to calculate both terms because even if one is above 50%, it does nothing but the other.
Exactly. Because, when you calculate this one and this 0.2, you're not done because you didn't do the normalization constant. So you have to do this term, and you have to do both of them otherwise. Or alternatively, you could go and figure out what the normalization constant was, but we don't like to do that. We like to avoid the normalization constant. Yes.
So can we use these results in like an actual probability context comparatively, like saying it's twice as likely that they like it than we don't, or do we only say that we predict that they don't get it?
At the moment, all your job is to say predict they like it or not. But it turns out you could, in fact, take these two numbers and figure out what is the normalization constant.
Okay.
Because remember, the normalization constant will be whatever constant, this thing was divided by. If we use the fact that we knew that the two probably should add up to 1 and that they have the same normalization constant, once you have these two numbers, you could backwards compute if you wanted a probability. So yes, we could get more insights, but our job is so simple. Predict a 0 or 1 for now. Okay? But this isn't the real Bayes. But it was just great. That was fantastic. There's like nothing wrong with that theory. It was a really good way to make prediction. Are you guys ready for brute force Bayes m equals 2? What's m? It's the number of features per user. And by features, I mean how many inputs do you have per user. Now I've got 2 users. We're throwing in Zootopia. So now you're going to predict whether or not somebody likes Life of Beautiful, but not just based on Independence Day, also based on Zootopia. And we're going to use the same theory. We're going to be like, okay, I'm going to either predict a 0 or 1 based on which one of these makes this term the largest, the probability of y given my inputs. Seems like a very nice theory to start out with. I like it. Mwah, fantastic. And then we get to use Bayes. That makes me so happy. You guys know whenever I get to use Bayes, like a little warmth in my heart grows. So we're very happy here. This is a great theory. We get to use Bayes. And it leads to this expression. And one of the things that makes us so happy is that the only thing we don't like about Bayes is normalization constant. But because there's an argmax here, we don't even need to bother with the normalization constant. Whatever value this is, it won't change which argument maximizes the expression. And therefore, we just need to calculate this. This is exactly the same as when m equals 1. But now it's worth recalling that x is a vector. And in this case, remember that x will have 2 numbers because there's now 2 movies that are in our inputs. Making sense? Okay. So what are you going to do? This is the joint probability of them liking movie 1 and movie 2, given x. And when you hear joint, you should be like, ooh, joints, don't those get big? They do get big. Well, let's look at all our parameters. This doesn't include the parameter for probability y. I'm just looking at all the parameters you need to be able to compute this expression. To compute this expression, you have to say, if y equals 0, what's the joint probability of any combination of x1, x2? If y equals 1, what's the joint probability of any combination of x1, x2? But that's not so bad. We have 8 parameters for this term. 2 more for this. We've only got 10 parameters. That's not too bad. And if you want to estimate all of them, you could do that based on data. You can say, counting based on probability that y equals 0, I could count for each of these and come up with a pretty reasonable estimate. Fine, not a big issue. Brute force Bayes m equals 3. We're throwing in a random TV show. And now we have to make our prediction. Same theory. Starts with that wonderful place of, let's just predict whichever one's most likely given the inputs. Then we can use Bayes' theorem and rewrite this, and we can get rid of the normalization constant. Fun times like we've always been having. And the only thing that's different now is that x is a list. It will have whether or not they like movie 1, whether or not they like movie 2, and whether or not they like movie 3. And we'll talk about the probability of all 3 of those given y. So we're going to have a parameter. If y equals 0, I'm going to have to know the probability of the joint assignment of x1, x2, x3 in that case. So if y equals 0, I couldn't make a 3-dimensional table. But if I could, I would have put a 3-dimensional table here. A 3-dimensional table would say for any combination of x1, x2, and x3, I guess that is a 3-dimensional table. Well, okay, any combination x1, x2, and this is for x3 equals 0, and this is x3 equals 1. There's these 8 values to represent the case where y equals 0, and 8 values for the case where y equals 1. Ooh, 16 parameters now. That's fine. 16 parameters is not a problem. We've got millions of users. We can estimate all 16 of those parameters. Just counting. What if m equals 100? Well, we go back to our lovely little theory, and it starts with the probability that y is 1 or 0 given x. Fantastic. We use Bayes' theorem. Fantastic. That makes us happy. We get rid of the normalization constant. We do our little normalization constant as gone dance. And then we end up with this final expression, and we're like, okay, this just needs us to have a parameter for the probability of any assignment to the 100 movies given y. You're like, oh, actually, Chris, that might be pretty big. There might be quite a lot of parameters. How many parameters would there be? And one way to answer that question is, if y equals 0, how many unique assignments could you make to x1, x2, x3, x100? Because you'll need a parameter for each unique assignment. Somebody who hasn't said anything yet today? Yes. A lot, yes, there's so many. Do you want to get more specific? We can walk through it together. Okay, x1, what are the values that x1 could take on? Exactly, 1 or 0. So, okay, there's two choices here. What are the values that x2 could take on? Yeah, and no matter what x1 is, x2 could still be 1 or 0. So there's two choices here, two choices here, two choices here, and there's two choices for that 100th one.
2 to the 100.
2 to the power of 100. Uh-oh, that's a lot. 2 to the power of 100, and that's just for y equals 0. You'll need another 2 to 100 for y equals 1. So it's actually technically 2 to 101. Woof, that's a lot. Oops, we have more parameters than number of atoms in the universe. I hate when that happens. That's going to take a lot to estimate. There might be a lot of people on Netflix, but there's not that many people, and now there's Disney Plus, so there's like other issues. Big O for number of parameters. So if m is your number of features, and every feature can either take on the value 0 or 1, this brute force Bayes has a problem because the number of parameters will be big O 2 to the power of m, and that's just too much. So even assuming each feature is binary, this is not going to cut it. Brute force Bayes, you were so kind to us. You tried so hard, but you tried to use too much force for what should have been a more delicate problem. Okay, a pedagogical pause, think about your life, have 2 minutes, try and summarize what we've learned so far. If there's something confusing, come ask me, or if you need to run to the bathroom, go run to the bathroom. I'll give you guys 2 minutes. And if we could switch over to music, I'm going to try and play. Okay. So, just to bring us back to the plot line, this was going to be so cool. We had this great idea. It was going to allow us to completely calculate whichever choice of 0 or 1 would maximize the probability of y given s. What a good idea. It just ran into this problem that this term here is in fact talking about the probability of the joint assignment to x given y. And when computer scientists came across this problem, they're like, well, that's exponential. That's going to be a huge problem. And in very computer scientist fashion, they're like, well, let's just hack it. And they came up with an assumption that is so wrong, it might shake you to your core. But an assumption that is so helpful is going to make this very, very straightforward. They called this assumption the naive Bayes assumption. And here's what the assumption is. This is hard to calculate. What if we just assumed that every value of xi was independent of each other, conditioned on y? So if you tell me whether or not somebody likes Life is Beautiful, I'm going to assume that whether or not they like every other movie is independent of each other. Now, first of all, if you make that assumption, it's got this sweet, sweet payoff that this hard term becomes the product of a bunch of much easier to think about terms. It's the product of thinking about each movie x on its own given y. You don't have to think about anything jointly once you assume independence. So that's the good news. What's the bad news? Is there any? Yeah, there kind of is. The bad news is that's not right. That's not true at all. Like, let's say this is whether or not somebody likes Zootopia. And then this movie is whether or not they like Zootopia 2. Like, are those truly going to be independent of each other? No, whether or not you like Zootopia 1 very much changes whether or not you like Zootopia 2. Now, the assumption says like, but if you condition off whether or not they like Life is Beautiful, then it's mostly independent. And it's just wrong, but it makes the math really sweet. Question?
When we deal with most data points in a sample, don't we always assume independence anyway? So why is it so awful in this case?
Yes. What we assume, we've always been assuming IID samples. And to be clear what that means is if we go back to our data set. Where's my mouse? There's my mouse. So if we go back to our data set, the IID sample assumption is saying, I assume user 1 is independent of user 2. And they come from the same distribution, so maybe the data points can have some relationship because they're coming from the same distribution, but I assume that they're independent from one another. And assuming that people are independent is pretty reasonable. Everyone's very happy with that. It's once you start assuming that the features are independent that it becomes a little bit like, ooh, that's actually pretty wrong. Every assumption is wrong on some level, but users being independent is a lot less wrong and something we're much more happy with. And features being independent feels very, very, very wrong. Does that make sense? It's fair to think about each person being an independent pull from the distribution. Think about your people in Bhutan. We assume that every pull is an independent pull from the distribution, and independence of each pull is a very reasonable thing. So it's a great question, but hopefully I gave some clarity there. Okay, I'm seeing a nod. Okay. So parameters in the universe, pedagogical pause, naive Bayes assumption. Okay, so this is the last great idea. And if you incorporate this great idea, you'd have naive Bayes. So we'll just take a little bit of time to unroll what this idea means. But just to be clear, naive Bayes is going to use the same correct mathematics that we've been using this whole class, and then it's going to make a very wrong assumption that the joint probability of your inputs given the thing you're trying to predict is equal to the product of the probability of each input feature on its own conditioned on y. So remember, each x sub I might be a particular movie. So this is the joint probability of all movies in the inputs given y, and this is thinking about each movie on its own and just multiplying. For those of you guys who are a fan of Bayesian networks, there is an implied Bayesian network here. The implied Bayesian network is there is a random variable for which is whether or not you like the target movie. And we're going to say that each of the input movies are random variables, and Each of those random variables are caused by whether or not you like the target movie, but they're not affecting one another. That's what it would look like if you were to draw it as a Bayesian network. And particularly, this Bayesian network tells you the joint probability of somebody liking the target movie and liking the input movies. It says it's going to be a probability that you like the target movie times the probability that you like the input movies given the target movie, which becomes a big old product. Wild. And this leads to a naive Bayes classifier. Naive Bayes starts exactly the same way brute force Bayes did. This GX is just a fancy thing people use when they're talking about your machine learning algorithm. You can ignore it for now, but you can just say the prediction I make is whatever value 0, 1 makes this as the largest. So if y equals 1 makes this largest, we're going to predict a 1. Bayes' theorem allows us to flip this, and because argmax gets rid of the normalizing constant, we only have to think about the numerator. And then if we employ the naive Bayes assumption, this is no longer the joint probability of all of the inputs given y. It's the probability of each feature on its own given y, all multiplied together. And then this term is exactly the same as before. And just to be clear, sometimes we're going to have numerical stability problems. So argmax of an expression is the same as the argmax of the log of expression. So a lot of times people will actually do log probabilities. And if you did log probabilities, it would be whichever value 0, 1 makes this expression the largest. Exact same thing as brute force Bayes, is just when you come to calculate the probability of the inputs given y, we're going to use this naive Bayes assumption. Let's break it on down. You still need to do training, but training becomes much easier. You have to estimate the probability that y equals 1 and the probability that y equals 0, and that will just be counting. If you want to know the probability that y equals 1, it's just out of all your training examples, how many had y equals 1? Not that complicated. If you want to estimate the probability that xi equals 1 given y equals 0, then we can just use conditional probability counting. Hey, take all your examples where y equals 0. How many of those, what fraction also had xi equaled 1? That's MLE. MLE says you should just do this counting. MAP, that really complicated extension. You guys ready to see how MAP changes from MLE? Made a big deal about it. Bloop. This is MAP with a Laplace smoothing, which sounds so fancy. Is that the fanciest way you've ever heard of somebody say, add 1 to the numerator and add 2 to the denominator? Anyways, it just has this prior belief that we've seen at least one example of y equals 1 and one example of y equals 2. Therefore, it just adds 1 to your counting in your numerator and 2, both for the y equals 1 and y equals 2 case to your denominator. And same thing over here. You add 1 to the numerator and 2 to the denominator. That's the Laplace prior, so beta 2, 2. We have ways now to estimate all of our parameters. And I'd like to take a moment to just show you how you could use this. So let's imagine a case where x1 denotes likes Star Wars and x2 denotes likes Harry Potter, and now we're going to try and predict the variable likes Lord of the Rings. Yes, this is the nerdiest of movie examples. What are you going to have to estimate? First of all, you have to estimate the probability y equals 0 and y equals 1. If this is the number of people who had y equals 0, and this is the probably number of people who had y equals 1, then to estimate these using MLE is just going to be counting. It'll be what fraction had y equals 1 and what fraction had y equals 0. Then we need to calculate the probability of x1 given y. And for x1 given y, we can think about all the cases where y is 0 and x1 is 0. All the cases where y is 1 and x is 0. And if you do MLE, it'll just be counting to figure out that, here, there's 13 people with y equals 0. And out of those, 10 out of 13 had x1 equals 1. There's 13 people with y equals 0, of which 23% had x1 equals 0. For both of your movies, you'll create a table that's a 4x4. And this is going to be true. If you had 10 movies, you just have 10 tables that are 4x4. It's going to scale very nicely with number of movies. Cough, cough, naive Bayes assumption. We know you're doing something wrong, but I get that you're making it easier. So now somebody actually walks in and they say they like Star Wars, but they don't like Harry Potter. And now you have to predict whether or not they like Lord of the Rings. Again, we're just going to be using the brute force Bayes idea. It's just when we get to this term, we're going to use a naive Bayes assumption, which says we're going to think about each feature on its own multiplied together. So we need probably that x1 takes on the value 1, given y. x2 takes on the value 0 given y, and the probability of y. We'll try this both for y equals 0 and y equals 1, and we'll choose whichever one is bigger. So it'll be the argmax. We put in x1 is 1, x2 equals 0. We try what happens when y is 0, and we get this expression. We can look up all those terms, multiply them together, get a number. We can think about when y equals 1, and then you get, okay, yes, they liked movie 1, they didn't like movie 2, and now we're thinking about the case where they do like the predictor movie, y equals 1. And then again, it's 3 lookups. For each of these probabilities, we've got a parameter. We can look them up in our tables, multiply them together, and we get another number. Notice these 2 numbers don't add up to 1 because we dropped the normalization constant, but it'll still be the case that whichever argument y equals 1 or y equals 0 maximize this expression will be our prediction. In this case, y equals 1 maximize the prediction. So in this case, probably that y equals, or we'll make the prediction that y equals 1. I mentioned this in words earlier, but it's worth restating. There is a normalization constant. There's some constant we didn't think about here, and that exact same constant existed in the case where y equals 0. Because we know probability equals y equals 1 plus probability equals y equals 0 should equal 1, we could solve for what the constant is, and then you could figure out exactly what's probability y equals 1. But as I said, our job isn't to do that. Our job is to predict 0 or 1. Now, that was MLE. What if we had to do MAP? If we have to do MAP, we have to choose a prior. And what prior better than Laplace? Laplace is for every probability P I'm estimating, I'm going to imagine one example of 1 and one example of a 0. So if I'm predicting a PI, I'm going to imagine one example of success and one example of failure, which is going to mean calculate how many times I happened divided by how many samples I had. So it's very, very similar. It's just, when you get here, instead of thinking about 13 and 17, we're going to add an imaginary trial for y equals 0, an imaginary trial for y equals 1, and carry that on for the x's. Long story short, that's naive Bayes. Training naive Bayes is as simple as counting. Actually, this should be for a binomial, not a multinomial. Training is just counting. Okay, a little bit of a fun aside. If you ever get an email like this, which is clearly spam, if you look into the metadata, especially at Stanford, you'll see something that looks like this. And it's hard to interpret, but at the very end, you might see something that says like 8.0 Bayes underscored 99. And then it'll have a tag which says the Bayesian spam probability is 99 to 100%. And you might wonder, what is Bayes doing in my mail server? And the answer to that is one of the first huge applications of naive Bayes was in spam classification. And fun fact, the person who did that was our very own Mehran Sahami when he was working at Google. Or I think this is before he worked at Google, got him a job at Google. And then they implemented it at Google, and using naive Bayes, they would try and predict whether or not an email was spam or not. It's a 1 or a 0 classification problem. And even though spam became more and more prevalent, as they got more and more data, they got better and better at estimating the parameters. They got very good, even using naive Bayes, at predicting whether or not something was spam. A source in case you're curious. So, if you wanted to predict spam emails, you could use this naive Bayes classifier. What you need to do though is you need to take each email, and particularly in your training emails, you have to take that email and turn it into X's and a Y. What are the X's going to be? Well, what they did is they took, in English, 100,000 words in English, and they would create their vector of X to be how many times did word 1 occur? How many times did word 2 occur? Or sometimes just whether or not word 1 was there or at all, whether or not word 2 was there, whether or not word M was there. So every variable xi was a 1 or a 0 whether or not that word appeared in the email or not. Now, just to be clear, M is huge, so they had to make this naive Bayes assumption if you wanted to do the spam classification really quickly for every single email that came in. In this case, what's y? So if x is the indication of whether or not every single word in English is in the email, y is going to just be simple 0 for not spam, 1 for spam. This is going to be trained. You're going to learn your parameters on historical data. And so what they did is they took a whole ton of old emails, manually decided if they were spam or not, and then we used those historical data to train all of their parameters. And you could have done this too. So if we flash back 20 years, you guys could have changed the world of spam classification just using what we learned in class today. And it's the exact same thing. Fun fact, they in fact used MAP with Laplace estimation. And one of the reasons that they wanted to use MAP with Laplace estimation is in their training data, it was very believable that there could be some word that doesn't show up at all for spam or not spam, which could lead to a probability of 0. And a probability of 0 becomes very problematic in naive Bayes because when you're multiplying all your probabilities of xi's together, so naive Bayes has this term, which has the probability of over I, the probability of feature I given the true label. If any single one of these terms ends up being 0, it just hoses the whole thing. It's like crash in the party. It's like, yeah, woohoo, we're all 0. I don't know, something like that. Anyway, so you don't want to have any of those terms be 0. It's very problematic. You lose all information if a single term is 0. And so actually this Laplace prior is very helpful. Laplace prior gives you the guarantee that no probability will either be 0 or 1. Okay, and then classification. A new email comes in. You would say, okay, which words are in this email? You would calculate the naive Bayes prediction, and then you decide, is this spam or not? What a fun time. And it basically comes down to this, argmax over the inputs given y times the probability of y, apply the naive Bayes assumption. And the naive Bayes assumption, just to remind you, is that this joint probability of your inputs given y, remember there's 100,000 of these, can just be thought of each input on its own given y. Okay, so training naive Bayes, estimating parameters just of Bernoulli's, and it's just counting. Okay, now, interesting question you might ask. At this point, we've kind of finished the plot line. We want to do ML, woohoo, let's do classification, yeah. Uh-oh, we can't just do the brute force Bayes, sad times. But if we make the naive Bayes assumption, we've got a whole pipeline. We can take a training data set, estimate our parameters. Then we've got a probabilistic model with parameters, which means if we get a new example, we can make a prediction. But there's one step I haven't told you about. How do we tell if our predictions are any good? Well, hopefully they're good because they're based on data, but maybe the y-hats and the y's are actually different quite a lot. What people do is they actually hold out some data that they call their test set. So you train on some data with spammy emails and non-spammy emails, and we're going to hold out a special set of data where we know the answer. We know if it's spam or not. And we use that to quiz the machine learning model you just built. So you just built a machine learning model. I've got a whole quiz to give your machine learning model. I've got all these emails, and I know if they're spam or not, and I'm going to test the machine learning model. I'll give the machine learning model each email one at a time. And you'll predict spam or not spam, and then I'll see if you're right. And if I take this whole quiz and I give it to machine learning model, we call that testing. And there's a couple of numbers that people really care about. One is accuracy. What was your raw score on the quiz? Like if there was 100 emails in the quiz, did you get 90 correct? That would be an accuracy of 90. If there was 10,000, you got 9,000 correct, that would still be an accuracy of 90%. There's two other numbers that people sometimes care about. One is precision and one is recall. And basically, recall says, how well do you do at predicting when we think about you actually have spam. So when something is spam, how good are you at pulling it out? That's the recall. So out of all the quiz items that were spam, how well did you do? So on that particular subset. Precision means, hey, you told me something was spam. So take all the quiz items where the ML model actually predicted spam, and how well does it do when it predicts spam? And you can think about that as, if it says spam, should you trust it? And this is, if it really was spam, did it find it? They're kind of clunky ideas to get your head around, but people do really care about these. And one way of telling you this is, precision gets close to 100%. Like people got really almost perfect on this measure of the quiz. And recall was pretty high. What does precision mean? Precision means if I say it's spam, it is spam. And why might you care about that? Because you don't want to take that very important email and call it spam. So precision means that when the machine learning model says it's spam, you can trust it. It probably is. And recall means that if this was 100%, no spam would end up in your inbox. And if it's less than that, some spam will actually make it into your inbox. And at the time that they were using naive Bayes in Gmail, they were getting really high recall rates, not 100%. Now, just to be clear, just using words as features was pretty good, but it turns out if you look at a couple other things like who is the sender, is the email signed properly, all those things were extra features that they threw into their naive Bayes. And there you have it. So, in summary, you have learned naive Bayes classification, and you will go build it. When you go build it, here's what I want you to know. Training is just counting. You have to estimate all of these parameters, but it will be just counting in your training data set. MLE is pure counting, but it doesn't take into account the fact that maybe you want to imagine some successes and failures to avoid probability of 0. MAP just adds in a couple other cases. Once you've done your parameter estimation, you can make your prediction by doing the argmax of the probability of y times the probability of each xi given y. We will often use logs to avoid numerical underflow when it comes to computers. And that is the end of the story. And you know what that means? I'm pretty sure this is your last class, which means I'm pretty sure we can start Thanksgiving break 2 minutes early. Have a fantastic Thanksgiving. I'm so thankful for all of you guys. Thanks for working so hard in CS109. Have a great break and see you back when you're done.